water quality is defined by a multiplicity of parameters, describing the presence of organic and inorganic compounds as well as of microorganisms. Many of these parameters are easy to measure and could be defined as low informative parameters, since they cannot be clearly linked to a contamination event or to an adverse effect for human health. We are, for instance, talking about pH, conductivity, absorbance, and turbidity. However, sensors are available also for online measurements, permitting to have a high-resolution monitoring, such as a measure every minute. Other parameters are high-informative parameters, identifying compounds whose concentration values are for sure the consequence of a contamination event, or compounds which are considered toxic. To make some examples, among chemical compounds, we are talking about heavy metals, chlorinated solvents, pesticides, some disinfection byproducts, emerging contaminants such as PFAS and pharmaceuticals. Among microorganisms, we can cite E. coli, Enterococci, Legionella, and protozoa such as Giardia and Cryptosporidium. These parameters require sophisticated laboratory instruments to be measured with a high effort and cost, and often require many hours to obtain a concentration value, which become many days and sometimes weeks in case of microbiological parameters. No online sensors are available for these parameters, and measurements are performed in laboratory on-grab samples. Therefore, the time resolution is very low compared to the one of low informative parameters. It is intuitive that the time lag between sample collection and analysis and the availability of the measured concentration values represents a strong constraint for real-time controlling the water quality, the treatment process's performance, and the distribution network. The solution to this issue would be represented by having high-resolution monitoring of high-informative parameters to be used as backbone of an early warning system about water quality, or to manage removal processes in a more sustainable way, meaning saving chemicals and energy and minimizing potential drawbacks, such as disinfection byproducts formation in case of disinfectant overdosages. A possible solution to this issue relies on machine learning, which permits to develop soft sensors predicting high informative parameters, exploiting the information hidden in high-resolution, low-informative parameters. Soft sensor stands for software sensor. The value of a parameter in a predefined time instant and sampling location is virtually estimated by a combination of the values of other parameters measured in the same time instant and in the same sample location. It is important to stress that this combination is highly nonlinear, since it has to capture physical and chemical phenomena linking the various parameters, as only machine learning is able to do. To understand how we can do this wizardry, I leave the floor to Francesco.
Actually, this is no wizardry at all, but the careful extraction of the relevant information using the data coming directly from the phenomenon. Indeed, the problem of predicting a value on the basis of the ones of correlated measurements is the classical example of a regression problem in the machine learning field. With such a technique, we aim at approximating the relationship between a set of input and an output value, only relying on the data, composed by the input-output couple observed in the past. If the relationship is stationary over time, the information contained in the past data is able to predict what will happen in the future. The process of approximating the relationship corresponding to the real process starts by selecting the appropriate family of model, capital F, of possible function, which should contain models, f', f', etc., that are flexible enough to mimic the original input-output relationship. After that, we need to set a loss function L that tells us how much a specific function is fit for the approximation task, according to the data we have on the problem. The smaller the value of the loss, the more the chosen function is appropriate for the task. Finally, we need an optimization method to efficiently search in the model family set the function which is the most suited for the specific task. In this specific problem, the family that has provided the best performance is the neural network one. These models are based on the connectionist approach, whose idea is that the appropriate connection of multiple simple models is able to provide a flexible approach to solving the problem of approximating input-output relationship. In our case, the base model is the perceptron, a unit in which the value of the output, 0 for low and 1 for high, is determined by the linear combination of a set of inputs and the transformation of a nonlinear function. The use of multiple units of the perceptron, displaced in layer and combined by a set of weights, allows modeling a wide variety of relationships, even the ones presenting nonlinear behavior. A single element in the family of the neural network is determined by the values of the weights, which should be learned from the available data. Among the possible losses, the most common one is the quadratic one, which weights in the same way positive and negative prediction error, penalizing more the ones which have a large value. Finally, thanks to the layer structure, one can apply a simple method called the backpropagation algorithm to choose the most appropriate weights for the network in an iterative way, by evaluating the error of a network on a set of samples and updating them accordingly. The process of finding the best neural network in the family is commonly called training. Once the training is done, the network is used to make predictions on the values of the output, in our case the concentration of a high informative water quality parameter, by measuring only the input values, in our case the low informative water quality parameter. This phase is commonly called the prediction step. This approach has been applied, for instance, to the data characterizing the effluent of reclamation urban wastewater treatment plant. In this specific case, the concentration of Escherichia coli was the target of the prediction task. The application of a specific neural network model highlighted that the machine learning-based model is able to provide accurate enough prediction. The ones near the bisector on the figure have low prediction error, and allows to have a real-time prediction of such a concentration. This allows for the application of high-frequency control in water treatment. Similar studies also provided evidence that using the neural network approach to select the amount of disinfectant to be dosed for the Escherichia coli concentration reduction provides a significant saving from 50% to 55% with respect to traditional strategies, which are de facto uncontrolled strategies, only aiming at maintaining the Escherichia coli below the threshold set by law, not caring about the environmental externalities and costs. The previous example shows how the application of machine learning to the monitoring of water contaminant concentration is a promising direction, and thanks to its generality, how it can be applied to provide a reliable prediction of contaminants. However, this is only the first step toward the complete integration of automatic data-driven approaches to the field, and constitutes a valuable research area for future studies.